Alright, I'm gonna start the meeting.
No problemo.
Yeah, even though it's three of us, four of us here, it's okay. So,
A motherfucking PowerPoint. Let's go.
yeah.
He's recording.
Pop off, Tim. Oh, my bad. Recording.
Oh no, it's cool. It's cool. It's not formal or anything, you know. So, first, I want to start off with some news about the chassis.
Broken.
So we were actually able to get the chassis from the lab on Wednesday,
Sick.
and I'm planning to go over to Richard's house to count all the parts and see what kind of quantify what parts that we have and put them on a list for you guys. So that's that. And today I will be going over the design and vehicle dynamics, which Jovan and I actually kind of started already. So
Mamas.
yeah, this should be really familiar to you, but I'll be like going over all the forces and stuff like that. Okay, so design and vehicle dynamics. So it's important to understand how you build the robot affects the vehicle dynamics. So you should think about like weight distribution, the constraints, available materials and tools. So the fewer parts that you have, the simpler, the less money, time designing and manufacturing that you have to do. So in our case, like we don't really want to over engineer something because that's going to take more time and more resources. So just like keep in mind that we have like less than a year just to design, manufacture, and test the robot. So if we do have something that needs a lot of engineering, it might take 2 years, or if we have enough people, we might be able to do it in one. But usually you want to stick to like the minimum. Yeah. Okay, so forces on wheels. So torque. What is torque? It's the rotational equivalent of linear force. So torque is equal to radius times force, as you can see in the picture on the right. So the perpendicular distance times force. And with this equation here, we can see that if you increase the wheel size, you actually get decreased acceleration because there's less force on the wheel. Right? And
Wait,
same
what?
thing. Yeah, so if
Mind
you
fucking blown.
Yeah. No, because
so
I'm kidding.
the radius of the tire, right?
Because
yeah,
the torque will remain constant.
yeah, exactly.
Because if you think about it, well, this is how I thought about it when I first learned it.
Don't think about it. I'm kidding. Go ahead.
if you increase the size of the wheel, wouldn't you have to put more force on the wheel?
If you have more torque,
Yeah, if you have more
Oh.
torque, yeah.
yeah, so
Okay, I see.
you see it, right? So
Yeah.
if you increase the radius and you have the same amount of torque, your force has to decrease.
Because it's torque divided by. Okay.
Yeah, and then same thing for the other direction. If you decrease your wheel size, you actually get more force, but overall you have less displacement. So this is kind of why if you have smaller wheels, you have like a really good acceleration, but you're gonna you win in the acceleration, but you kind of lose in the distance.
You're not covering much.
Yeah, exactly. So this is so an analogy is like people with shorter legs actually have better acceleration. So like when you're in football, you can actually like juke everyone out, but people with longer legs they can run, uh, they can cover more distance. So kind of think of it like that. Yeah. So I'll be going over like 4 different forces that you guys have to account when designing your vehicle. So these calculations kind of come after the design process. So this is just to give you guys like an overview of what you guys need to do after we pick the iteration. So the first force is rolling resistance. So what is it? So it's pretty much the energy needed to maintain a constant speed or the force resisting motion when it rolls on a surface, right? So that's the definition of rolling resistance. It's pretty much yeah, that's pretty much that. And what causes rolling resistance? So hysteresis is pretty much this curve here on the bottom. So depending on if you go to the left or the right, the hysteresis would be different. Plastic deformation and slippage. This is just like general terms. But yeah. So the resistance force is equal to the rolling coefficient times your normal force of the wheel. Right. So depending on what iteration you have, you might have a different normal force here. And the rolling coefficient, it's usually you would test it to get that coefficient, but in our case, we have to look for that number. So it's different on pavement, on grass, on water. You have like different rolling resistant coefficients. Yeah. And then we have gravity force, which is tied to the center of gravity. So this is based off of the weight distribution of the robot. So this directly affects the axle loading. And yeah, and the lower center of gravity provides better stability, but this is just like an extra fact about it. So you can actually find this force here by doing statics. So if you take the moment about A, you could get the force here on this axle, and then you can take the summation in the y direction to find your other force here. Yeah. Yeah, and then so gradient. So what is gradient? It's pretty much the ratio of rise over run. So we have an equation here that can find your slope gradient. So your slope gradient is equal to rise over run. It should be like a triangle times 100. So in our case, in the rules, they say that we have a 15% gradient, right? So which is equivalent to about 8.5 degrees. And when you're going up a slope, the forces kind of change. So if you want to get the axle loading, you would need to use this equation, because since the center of mass is here, you just take the moment about, let's say, this point here to find your force here. And there should be 3 moment forces. So we have the center of gravity in the X and Y direction, and also the force on the rear tire here. Yeah, that's pretty much that. And then if you want to find the kind of like the grade resistance for the whole vehicle weight, you'd use this equation here, which is force is equal to weight times sine alpha. Yeah. Does anyone have any questions, or is it kind of straightforward?
You're blowing my mind right now, Tim.
Yeah. Dude, you know Baja and Formula go over this. So we're pretty much doing what they do. But ours is like a robot, so it's a little different, but we can apply the same
concepts.
Yeah. Yeah. So next we have aerodynamic / drag forces. So what is drag? So drag is the force acting in the opposite motion of an object moving in a fluid. And that can be seen with this equation here. So the force of the drag is equal to 1/2 times your drag coefficient times area times density times velocity squared. So I would say in our case, since we're not moving at a fast speed, that your aerodynamic force is kind of small. But I think it's something that we should take into account as well. Yeah, so just keep in mind this aerodynamic force when you're building your robot. And then I think the last force is acceleration force. So this is the force necessary to accelerate the vehicle from a complete stop to maximum speed in a desired time. So we know that force is equal to ma, right? And you can actually break that down into, so mass turns into weight times gravity, weight over gravity, and your acceleration turns into velocity over time. And so essentially, you can play around with the time required to achieve maximum velocity, and that'll change your force as well. So if you want to accelerate in 1 second, you would have like a value. But if you put it in 0.5, you need like twice the force. Does that make sense? Right. And so determining the total wheel motor torque. So it's something called the total tractive effort, which is basically all the forces combined. So basically, when we put all the forces together, it's essentially this force here. So this is a total tractive effort. So we can plug it back into our torque equation. So it'd be the radius of the wheel times your total tractive effort or force times your resistance factor, which is like usually like frictional losses that you have to take into account. This is like an assumption. So usually it's between 1.1 and 1.15, but we won't really know until we actually do some testing. So yeah. Yeah, so some tasks for the mechanical team. So I want you guys to start practice mating in SolidWorks, get familiar with that. And so next Wednesday, I'll be able to go to Richard's house and count up all the parts and put them in a list for you guys. And then you guys can start designing your own iterations. And also I'm going to post an Excel file. So when you build your iteration, I want you guys to keep track of certain things. So for example, right here, you have the total size of the robot, the total length of T-slots, the center of mass, the drive wheel tire distance from each other, and the gross vehicle weight. And if you guys are confused on that, don't be afraid to ask for help. I can help you guys out. And then we also have this compliance sheet. So pretty much these are like the necessary components that we need to pass. So for example, like we need a camera mount, the LiDAR, the battery mount, the payload, the electrical compartment, passive wheels, acrylic, mechanical e-brake, and rules. So if your iteration does not have any of these, it is not qualified into the iteration. So you need to have all of these. So you guys have to take into account like these necessary components. And yeah, that's pretty much it. Does anyone have any questions?
So you want us to start doing that next week or this week?
Yeah, so once I get the parts, once I count up all the parts from Richard, then you guys can start designing your own iteration.
Sweet.
Yeah.
All right, that's A. And B, will be how will we be doing this? Will we be doing it individually? Will we be splitting up into teams or?
That's up to you guys.
Okay.
Yeah, because if you want to create your own iteration or work with someone, it's entirely up to you. It's like free for all, basically. But just know that I think we're gonna have about 3 weeks on this to pick an iteration.
Got it.
Yeah.
Got it.
And when it comes to testing, I understand that, like, I mean, obviously we're planning on doing testing. And it'll be obviously after the design process, once we pick our iteration.
Mhm.
Then are gonna have us like design testing. Will you be part of that? Because I mean, I understand like some of the testing you already kind of like mentioned, like finding the total tractive effort, et cetera, et cetera. Whatever you just said. But some of the other things that we might want to consider is probably like vibrations. If there's any way for us to do vibrational testing, um, I wouldn't want to do load because I don't want to break our shit, to be honest.
Yeah, yeah.
Put way
That-
too much stress.
That's a good point that you mentioned, Jovan.
Yeah.
About vibration.
Yeah.
So I'm actually still looking into how to test vibration on the chassis because I think that's like entirely up to testing, right?
Yeah.
So yeah, I'll get back to you on that. If you have an idea, you can mention that right now, but I'm still looking into that.
Nothing very concrete, like literally nothing. I'm thinking about like essentially building a system that we could like attach our chassis to, where it vibrates, obviously. Yeah, I have literally nothing concrete, so I can't say anything, to be honest.
Yeah, I was thinking we could just maybe we could put a sensor on it, and then that'll just track the like the y-axis or something.
Yeah.
You know, I don't know, but
We'll see. We have time for that.
yeah, we'll figure it out in the next month or something.
Mhm.
And then as far as the camera mount goes, like the anti-vibrational mounts, I'm still looking into that. Um, it's I wouldn't say that. So making the frame comes first, and then we can focus on the vibrational mount, the anti-vibrational mount. So yeah, and that's pretty much it. Um,
Let me see if I have any other questions. I think those are the only two questions that I had.
yeah. So let's see. So typically, for your total tractive effort, in our case, if it's a low speed vehicle, you actually wouldn't have to take into to account aerodynamic forces. So it'll just be 3 forces here. But if you want a more accurate answer, the more force that you actually take into account, the more accurate your required motor torque will be. So yeah, and you can actually do all these calculations on Matlab. So it's something called mathematical modeling. If you guys don't know how to use Matlab, I can kind of guide you guys, but because these are assuming that these are static forces, so these I think this is like the maximum force. But usually when you drive a vehicle, it kind of changes in terms of time, right? You can actually do that on Matlab. And yeah, so yeah. Um, yeah, that's pretty much it for this week.
And if you guys do want to like literally start doing it like right now, like designing the chassis, et cetera, we do not have the parts list. What I could give you guys, like by the end of today, is like a preliminary approximately how much of each parts we have. It will not be accurate whatsoever. So at the end of the day, we're still gonna have to wait for Tim to finish that part in order, for us to do it. But if you guys really want to like start like immediately, I could probably have that out by the end of today. Like I said, it will not be accurate, but it will give you a pretty good idea of what we have.
Yeah, actually, yeah, that's a good idea. So you guys can start practicing your mating on assembly.
Yeah. And if you guys need any more information about like some of the parts that we have, like the T slots, like where to get the T slots, you get 3D SolidWorks downloads off McMaster. So I can give you guys a link for that as well.
Yeah, McMaster.
Um, but yeah,
helpful.
yeah, I'm gonna have that done by today, and I'm going to post it up in the mechanical Discord.
sure.
So if you guys feel like you guys are ready to start designing your own chassis or whatever, you guys could do it right away. Like I said, before an accurate like what we have type thing, wait for Tim on that.
Yeah. Yeah. So okay. So on Wednesday, so when I'm going to make an Excel sheet of the quantities of each part. So for example, like we're gonna have like 3 6-inch T slots and then like 10 16-inch T slots. So you're gonna use these parts to construct your own iteration, if that makes sense. So basically, you guys don't want to create a new length of T slot if it's not there. You guys can use increments of 1 feet that you guys can buy from McMaster. But essentially, we're just recreating the chassis from our old parts because we have a new battery and it's a lot bigger than. So basically, our chassis can't. It doesn't fit the battery well. It kind of like protrudes in the top, and basically, you have to design your chassis around that. Yeah. And yeah, that's basically it for this meeting. I'll keep you guys updated throughout the week. Yeah.
And you say we have 3 weeks by this week or 3 weeks by like once we get the parts list
From today,
from today?
because
All right, that's fine.
we're going to meet up with Dr. Shin in about 3 weeks, right?
Oh yeah, that's right. Yeah.
Yeah, so we kind of have like a hard deadline of three
Okay.
weeks.
Then yeah, I'm gonna go ahead and get you guys the preliminary parts list by today.
Sounds good. Move on. Yeah. Do you guys have any last questions?
Where's Uriel?
I think he's at work right now.
Oh, whoa.
Yeah. So
And if you guys need help or have any questions, feel free to contact either Tim or I.
All right.
Yeah. Any confusion, don't be afraid to hit us up. We want to like give you guys like concrete information. Yeah, that's it for this meeting.
All right, cool.
All right.
Yeah.
Yeah.
All right, guys.
Yeah, sounds good. It was good seeing you all. I'll keep you guys updated, and yeah, I'll see you guys next week.
Yeah, peace.
Yeah.
Have a good one.